You move forward, you move sideways, you move up. 3 directions, 3 dimensions. It feels obvious, doesn't it? Like the structure of reality itself is self-evident, carved into the nature of existence. But here's what should terrify you. It didn't have to be this way. Here's the thing that should mess with your head. Math doesn't care about us. The equations that run the universe, they don't need 3 dimensions. They don't even prefer them. Honestly, the math is perfectly happy with 4, 7, or 11 dimensions. It still works. The geometry holds. Higher dimensional spaces aren't fantasy. They're mathematically consistent, logically sound, theoretically viable. There's nothing in mathematics that privileges 3. And yet, when you look around, when you reach out your hand, when you try to move in a direction that isn't forward, backward, left, right, up, or down, there's nothing there. So why exactly 3? This isn't a question with an obvious answer. It's not like asking why water is wet or why objects fall. Those are consequences of deeper laws. But the number of spatial dimensions, that's not a consequence. That's a parameter, a setting baked into the fabric of reality before the first atom formed, before the first star ignited. And we do not currently have a theory that predicts why exactly 3 large spatial dimensions exist. Cut to 1919. A mathematician named Theodore Kaluza drops a bombshell on Einstein. He wasn't trying to write sci-fi, he was just doing the math, solving Einstein's equations. And he discovered something wild. If you added just 1 extra spatial dimension, making 5 total dimensions, 4 spatial plus time, you could unify gravity and electromagnetism into a single elegant framework. The math was beautiful, the implications were staggering, but there was one problem. Where is that 4th spatial dimension? Kaluza couldn't answer that, and neither could anyone else. By the mid-20th century, physicists had gone even further. String theory, one of the most ambitious attempts to describe the fundamental nature of reality, doesn't just suggest extra dimensions, it requires them. Not 3, not 4, but 10 total dimensions for its equations to work, 9 spatial plus time. M-theory pushed it even further, 11 total dimensions, not as a quirky side effect, but as a necessity. The theories only make sense if reality is far more expansive than what we experience, and yet we remain locked in 3. Look, here's where it gets unsettling. If additional dimensions are not only possible, but mathematically required by some of our best theories, why can't we access them? Are they hidden? Compressed? Locked away in some geometric configuration too small or too strange for us to detect? Or is 3 dimensions not a limitation of our perception, but a fundamental constraint built into the universe's architecture? Because if that's true, then the next question cuts deeper. Why does reality collapse into this exact configuration? And more disturbingly, what would happen if it didn't? Before we go deeper into the mathematics that shattered our assumptions, I need to say this. Episodes like this aren't rushed. Every claim is checked, every argument rebuilt from the ground up, because when you question the architecture of reality itself, precision matters. Subscribing helps keep this work deliberate, human, thought through instead of churned out. If that depth matters to you, join us. Now, let's see what the math actually says about worlds with more than 3 dimensions. Here's what should keep you awake at night. The universe didn't consult physics when it chose 3 dimensions. Physics had to adapt. In the early 20th century, mathematicians began exploring spaces with more than 3 dimensions, not as abstract curiosities, but as serious geometric structures. They discovered something unsettling. The mathematics of higher dimensional spaces follows consistent, logical rules. 4-dimensional geometry, 5-dimensional geometry, even infinite dimensional spaces, they all work. There's nothing in the equations that says stop at 3, nothing that privileges our reality over countless others. The math works. It just does. Edwin Abbott, a Victorian schoolmaster, understood this instinctively when he wrote Flatland in 1884, a story about two-dimensional beings who couldn't conceive of a third dimension even as it existed all around them. The allegory was clear. If beings trapped in two dimensions can't perceive three, then what dimensions are we trapped inside, unable to perceive? By the 1920s, physicists weren't asking what if anymore. They were asking where. Theodore Kaluza's original proposal that a fourth spatial dimension might exist was expanded by Swedish physicist Oskar Klein in 1926. Klein suggested something extraordinary. Maybe the extra dimension isn't missing. Maybe it's curled up, compactified into a space so microscopically small that we move through it constantly without ever noticing, like an ant walking on a tightrope, perceiving only forward and backward, unaware that the rope itself has width. The idea seemed elegant, almost comforting, but it raised a darker question. If one dimension can be hidden, why not more? Here's the kicker. By the 1980s, string theory emerged, and it doesn't just ask for extra dimensions, it demands them. Superstring theory is only mathematically consistent in 10 total dimensions. M theory requires 11. Without them, the math falls apart. With them, it sings. So according to one of our most ambitious theoretical frameworks, the universe has 10 or 11 dimensions total. We're just stuck in the cheap seats, only seeing 3 spatial ones. But here's the betrayal. We have zero proof. Nada. No particle collider has ever detected a higher dimension. No telescope has glimpsed its curvature. No experiment has confirmed its existence. The extra dimensions required by string theory remain purely theoretical, phantoms in the equations, ghosts in the math. They must exist for the theory to work, but reality offers no proof. So either string theory is wrong, and one of our most ambitious theoretical frameworks is a beautiful dead end, or the extra dimensions are there, and we're simply incapable of reaching them. So this brings us back to the original question, now sharper and more urgent. Why are we confined to 3? Is it an accident of cosmic evolution, a byproduct of the Big Bang's initial conditions? Or is there something about three-dimensional space, something specific, something necessary that allows reality to exist at all? Because if the answer is the latter, then we need to ask, what happens in 4 dimensions that makes existence impossible? In 1917, a German mathematician named Paul Ehrenfest asked a question that should have shattered our sense of cosmic security. What if we lived in 4 spatial dimensions instead of 3? He wasn't being hypothetical, he was calculating, and what he discovered was horrifying. Ehrenfest worked through the mathematics of gravity, electromagnetism, and atomic structure in higher dimensional spaces. He wanted to know if the laws of physics, the forces that hold atoms together, keep planets in orbit, allow stars to burn, would still work if space had a different number of dimensions. The answer? Nothing holds together. In 4 spatial dimensions, gravity changes. It stops following the inverse square law and switches to an inverse cube law. That sounds like boring math, but here's what it actually means. Stable, long-lived orbits like ours become impossible. Under classical mechanics, planets can't maintain the delicate gravitational balance that keeps them circling their stars for billions of years. They either spiral inward and get consumed, or drift outward into frozen darkness. There's no sweet spot, no stable configuration where oceans can form, atmospheres can settle, life can begin. Solar systems become graveyards before life even gets a chance to blink. It gets worse. The horror doesn't stop at the cosmic scale. It reaches down into the atom itself. In 3 dimensions, electrons orbit atomic nuclei in stable shells because electromagnetic forces weaken predictably with distance. That stability is what makes chemistry possible, what allows atoms to bond, molecules to form, proteins to fold, DNA to replicate. In 4 dimensions, the Coulomb potential changes form. Quantum mechanical analyses show that hydrogen-like atoms become unstable. Electrons either crash into the nucleus or escape entirely. There are no stable electron shells, no periodic table, no chemical reactions, no molecules, no chemistry at all. Life, anything even remotely resembling complexity, is geometrically impossible. Ehrenfest didn't stop at 4 dimensions. He tested 2 dimensions as well. 2 dimensions? Even worse. You can't have a digestive tract in 2D because a tube running through you would literally cut you in half. You can't have neural networks complex enough for thought. Blood vessels can't cross without blocking each other. The topology is too restrictive. 2-dimensional space permits only the simplest structures, nothing that could think. Nothing that could wonder why. You fall apart. 3 dimensions, Ehrenfest concluded, might be the only configuration that allows for stable matter, complex chemistry, and organized structure. Not the most elegant, not the most mathematically beautiful, but the only one where existence doesn't immediately annihilate itself. This realization birthed the anthropic principle, the idea that the universe has the properties it does because if it were different, we wouldn't be here to ask why. But that's really not an answer, it's a loop. Yes, we exist in 3 dimensions because only 3 dimensions allow existence. But that just pushes the mystery one step back. Why does a 3-dimensional universe exist at all? If higher dimensional configurations are mathematically valid, why did reality stabilize at the one narrow setting where atoms can form and planets can endure? Was it chance? Or is 3 dimensions the only universe that doesn't destroy itself before the first second ends?
In 1998, physicists Nima Arkani-Hamed, Savas Dimopoulos, and Gia Diwali published a paper that changed everything. They proposed something almost unthinkable. What if extra dimensions aren't just theoretical? What if they're real and close? Not light years away, not hidden in some parallel universe, but potentially as close as sub-millimeter scales, though experiments have since placed strong limits on how large they could actually be. The idea is called large extra dimensions, and it works like this. Imagine space as a sheet of paper, our 3-dimensional reality. Now, imagine that paper is embedded in a higher dimensional space, like a page floating in a room. Gravity, unlike the other forces, might not be confined to the page. It might leak into the extra dimensions, spreading out and weakening as it does. And here's the kicker. This is why gravity is so weak compared to the other forces. Think about it. A tiny magnet can lift a paperclip against the gravitational pull of the entire Earth. Why? Maybe gravity isn't inherently weak. Maybe it's bleeding out of our reality into those hidden dimensions, leaving us with just the weak leftovers. If this is true, then the extra dimensions don't need to be compactified into invisibly small Planck-scale loops. They could be larger, still tiny by human standards, but potentially detectable. But we'd never notice them directly because we're locked to the surface, like insects crawling on a wire, perceiving only length, never realizing the wire has thickness. Experiments began immediately. Particle accelerators started hunting for signs of gravitational leakage, anomalies that would indicate energy disappearing into unseen dimensions. So far, nothing. But absence of evidence is not evidence of absence. The dimensions could still be there, just structured in ways that make detection impossibly difficult. Then there's the Calabi-Yau manifold, a geometric structure so complex, so alien that it exists only in abstract mathematics. String theory suggests that the 6 or 7 extra spatial dimensions required by the theory are compactified into these shapes. Space is folded and curled at scales trillions of times smaller than an atom. If you could zoom in far enough, every point in space wouldn't be a point at all. It would be a tiny, intricate labyrinth of hidden dimensions, invisible because they're too small, not because they don't exist. But here's what nobody talks about. If these dimensions are real, why are they hidden? Some unknown mechanism compresses them, confining them to structures so small and so inaccessible that even the most powerful instruments humanity has ever built cannot detect them. Was it a natural process, an inevitable consequence of how the universe cooled after the Big Bang? Or was it something else? A geometric phase transition that locked 3 dimensions into expansion and condemned the rest to collapse. And that leads to the scary question. If these dimensions are folded up, could they ever unfold? Because dimensions aren't static, they're dynamic. They can expand, contract, curve, and warp. General relativity proved that space itself is flexible. So if extra dimensions exist but are currently compactified, what would happen if they began to unfold? The physical constants we rely on would change catastrophically.
Imagine you're a character drawn on a piece of paper. You can move left, right, forward, backward, but never up. Not because up doesn't exist, but because you're fundamentally incapable of perceiving it. To you, the page is the entirety of reality. You have no concept of thickness, no language for height, no neural architecture to process a third dimension. And if a 3-dimensional being reached down and lifted you off the page, you wouldn't experience ascension, you'd experience annihilation. Now ask yourself, what if we're the drawing? A 4-dimensional being, if such a thing exists, would perceive our 3-dimensional universe the way we perceive a flat image. They could see your entire body at once, inside and out, without cutting you open. They would move through walls not by breaking them, but by stepping around them in a direction you can't point to. To them, you're just a flat sketch on a page, and we would never know they were there. This is the central horror of dimensionality. Perception is a cage. You can only experience the dimensions you're embedded in. A 2-dimensional being can't conceive of 3. A 3-dimensional being can't conceive of 4. The architecture of your brain, the structure of your senses, the framework of your thoughts, all of it is confined by the geometry of the space you inhabit. We are blind. The question, why does space have 3 dimensions, might actually be unanswerable, not because we lack the science, but because we lack the perspective. We're asking the question from inside the system we're trying to understand. A fish doesn't question water. A prisoner doesn't see the bars if they've never known freedom. But the physics gives us clues. 3 dimensions might be the threshold, the maximum complexity a stable universe can sustain without collapsing. 4 spatial dimensions and gravity tears atoms apart. 2 dimensions and complexity can't emerge. 3 is the Goldilocks number, not too restrictive, not too chaotic, just stable enough for matter to coalesce, stars to ignite, planets to cool, and conscious beings to evolve and ask why. This isn't design, it's survival bias. If multiple dimensional configurations were possible, we would only ever find ourselves in one that didn't immediately fail. We're not special. We're the statistical inevitability of whatever process generates universes, if such a process exists at all. But that raises the final, inescapable question. If extra dimensions exist, curled up, compactified, hidden in the quantum foam, then are they locked away by accident or by necessity? Because if three-dimensional space is the only stable configuration, then those hidden dimensions aren't just invisible, they're imprisoned, quarantined, sealed off from our reality, not because we're incapable of perceiving them, but because letting them unfold would unravel everything. We ask why three dimensions like it's a foundation, but maybe it's not a foundation. Maybe three dimensions is just the only cage strong enough to keep us in.